Okay, hello everyone, and welcome for this webinar session. Today we are going to talk about polymerization of microfluidic produced liquid crystal double emission. This is the topic of the webinar. So the idea today is that we will have a special guest. So let me introduce you the team who will be presenting today. So we have on our Fluigent side, we have Malik Soumaré, our customer support engineer, who will be presenting our technology to make double emulsion and making emulsion. Myself, Adam Mesian, marketing project manager at Fluigent, working on emulsion at Fluigent. And we have also Jan Lagawal from the University of Luxembourg, who will be presenting his work on liquid crystal double emulsion. So the idea is that he will make a presentation around his research field, introduce the cholesteric liquid crystal shell, the application around that. We will also after that introduce on our side the platform that we are using to make emulsion, and the platform that he is going to use in his experiment. And then we will switch to an interactive Q&A session. So we will have a dedicated Q&A session if you have questions. So for that, I encourage you to use the Q&A panel available at the bottom of the window, of the Zoom window. So please do not use the chat to ask questions. Please use the Q&A panel. It is better for us to handle the question, and it will allow us to answer each question and do not miss any question. Okay, so now I think it's time to start. Jan, I will give you the lead. You can start sharing your screen.
Thank you very much. All right, thanks a lot, Adam. Yeah, today I'd like to tell you about what you're seeing here in this movie. This is a cholesteric liquid crystal shell that my postdoc Yonggang prepared using Fluigent's microfluidics equipment. And you're seeing it as it appears in reflection optical microscopy. And you see it's changing continuously. So what Young is doing is changing the focus up and down. And this demonstrates quite nicely that these shells have very rich optical features. As I'll show you in a moment, these colors, they result from Bragg diffraction of light that involves both internal reflections, that's giving rise to the rings, and external reflections, which give rise to these spots and short lines that you see sometimes. I'll also tell you, of course, how you can make these shells. And to motivate a bit why this research makes sense beyond just the beauty and the physics, that is really interesting, I'll give you a glimpse into our efforts to apply these peculiar optical properties in anti-counterfeiting, in supply chain traceability, and in creating an infrastructure that is invisible to humans, but very visible to simple machine vision, and which in this way can support robots and augmented reality to better comprehend their surrounding. But of course, in order for any such application to be realistic, you have to transform these cells from the liquid state that is vital for allowing the microfluidic processing and the self-assembly into the structure. In that case, it's the liquid crystal state, to be specific. And we have to transform it into a long-lasting and sturdy solid state. And we do that by polymerizing the small molecular precursors. And this process of polymerization actually leads to some very interesting features as well, because you get shrinkage from the polymerization, and now you shrink a shell around a droplet that does not want to shrink. And you'll see that that gives rise to some very interesting effects as well. So this is what today's menu looks like. So first, I'll show you a little bit what are cholesteric liquid crystal shells and why are they interesting. And then I'll show you, give a bit of very quick description of how they are made, how they are processed, or not so quick description, but covering then the microfluidic shell production, of course, and the effects of polymerization and how we wash them and why that's important. Then I'll hand back to Adam to present the RayDrop platform. And finally, Xu, my PhD student, she's going to show some very recent results on how we are now starting to use this newest platform that's called the 𝗿𝗏 for making cholesteric liquid crystal shells. So let me first of all introduce the team. Just want to move this window a little bit. These are the people who work on this, and as I said, Xu, she will be taking over at the end to show some recent experiments. So first of all, then, for people who don't know liquid crystals, what are they? So liquid crystals are liquids formed by molecules that are anisometric, which means that they have an anisotropic shape. The most common is that they have a rod shape. And the remarkable thing with them is that these rods, they tend to align spontaneously along a common direction that we call the director. And this gives the whole macroscopic phase anisotropic properties that you normally only find in a crystal, a solid crystal. But here you have those properties, although it's a liquid that flows and that you can then process using, for instance, microfluidic technology. Today, I'll be focusing on a specific version that you get when you add a chiral dopant. So a chiral dopant is a molecule that has no mirror symmetry, so it breaks the mirror symmetry. And what happens to a nematic liquid crystal phase when you add a chiral dopant is that this direction of the molecule alignment, it starts rotating in a helical fashion. That's what's illustrated here. And effectively, you then get a periodic structure. And this periodic structure, because the helix is periodic, you can make sure that the period is on the order of the wavelength of visible light. And then when light enters a medium that is periodic at the scale of the light wavelength, you get this types of very strong selective reflection of a certain color. This is called structural color. You can actually see this in nature in many places. Many people hate pigeons, but if you look at them closely, you see that at certain angles, they have this striking green color. And at other angles, you don't see it. So that's an example of a periodic structure that gives rise to very saturated, strong colors, but it's often viewing angle dependent. And it's the same thing with the cholesteric helix. Because it's periodic, you get this saturated reflection of a certain color. And if you look along the helix, the color that is reflected is the longest wavelength. It corresponds to the period of the helix. But if you look at a certain angle away from the helix normal, then the color that is reflected is blue shifted because the effective period looks shorter. So that's typical for any Bragg reflecting medium. But because this is a helix, it's a chiral medium, there is another very important aspect, and that is that the reflected light is also circularly polarized. So not only do we have selection in color, we also have selection in polarization. And polarization is really important. We cannot detect polarization. Our eyes cannot detect polarization. But if you go to 3D cinema, you may be wearing these goggles, and what they are circular polarizers. So what they do is that they filter according to circular polarization. So in the cinema, they're actually showing two movies at the same time on top of each other, one for the right eye and one for the left eye. If you take off the goggles, because we cannot distinguish polarization, you see a very blurry movie. But if you put on the goggles, then the right eye sees only that part that is for the right eye, and the left eye sees only that part that is for the left eye. And that principle, as you'll see in a moment, is really powerful, and we can use that in many other ways as well. So how do we make the cholesteric liquid crystal shells? So first of all, I'll come in a moment, or let's say, first, what are cholesteric liquid crystal shells? So to give you an idea of the scale, it's on the order of 100 micron in diameter. The thickness is about 5 to 10 microns, or 2 to 10 microns. And inside is an isotropic phase. Usually it's water with some polymer stabilizer, and the same thing outside. And this thin layer then in between is the liquid crystal. What is important is that we're doing this, of course, on Earth. So we have gravity, and the two phases are almost never density matched. So that means that the inner droplet will tend to sink down or rise up. And that means that the shell will be thick at one point and thin at the opposite point. And you'll see when I talk about polymerization, as well as the optical properties, that this asymmetry that gravity creates is actually really important for the behavior. So as I said, the first example of this, this consequence is that these, if you look at the optical properties of these cholesteric liquid crystal shells, they actually have Janus-like characters. Janus was the Greek god, Roman god, I think, that had two faces. And this is the same thing here. So because this is a side view where you very nicely see that this is much thicker on this side than here. And if you look at from the side, you see this pattern with a central spot and a surrounding spot. And that's very similar to what you see also from the top. And this comes from, the central spot comes from light hitting at the center and then being reflected right back up. That happens at the longest wavelength because it's along the helix. The helix is aligned radially, as this cartoon illustrates. But if light hits a little bit away from the center, then if it hits at 45 degrees to the surface normal, that reflection is horizontal, and then it can hit another shell that then reflects light back up too, so we see it. But now you see the angle with respect to the helix is 45 degrees. So that means that the light is blue shifted. So the color that is reflected in this way, that is blue in this case, instead of red in the middle. So that's the top view type of reflection. If we instead prepare the shell so that the inner droplet is lighter than the liquid crystal, then you get this side view. So you have thin at the top and thick at the bottom. If you now look at it from the top, you see a completely different pattern. And that is because now the top is so thin that the light enters into the liquid crystal, and then you get the reflections inside the shells. And these can be quite complicated. You can have multiple internal reflections, but each of these correspond to a particular angle with respect to the helix, which filters out one particular color. And that's why you get these types of rings. So this, you can see that we get very interesting reflections that is due to this spherical shape and the asymmetric character. So we call these shells cholesteric spherical reflectors, or simply CSRs for short. And you'll see I'm going to use that abbreviation in a moment. So now to tell you a little bit about why these can be interesting, these are some examples of what these CSRs can look like after polymerization. So here we have a bunch of shells that are polymerized, and we are looking at them from the thin side. So we see rings, right? If you flip this over, exactly the same type of shells actually look very different, because now we have not the internal ring reflection, but this what we call cross communication between the shells, giving rise to these spots. And if you mix many different shells, some with longer pitch, because it's the helix period that determines which wavelength is reflected for each angle, and maybe of some small and some large shells and so on, then you get a very complex, rich pattern that can involve both the cross communication and the internal reflection, and of course the direct reflection. And these unique patterns is why we argue that these can be very interesting for thwarting counterfeiting and for track and trace of supply chains. Just a brief reminder that counterfeiting is really a very, very serious issue. You probably heard of counterfeit medicines. It's a huge issue. With the pandemic, we had issues with counterfeit vaccines also, but it affects everything from luxury goods to toys to seafood to pet food to airplanes parts. That's this example here. So it can be pretty serious. And what is our approach to do something about this? Well, what we're doing is that we are coating an object that we want to prove that this is original with CSRs in a random local arrangement. And the way to do this is we're basically dispersing these polymerized shells in a binder that is either curable by UV radiation, so it turns into a solid, or like a nail polish, solvent evaporates, and then you get a solid. And as this is solidified, you get a random arrangement of these CSRs. And because of these peculiar optical properties, that gives this particular object a unique fingerprint. And that is actually unclonable because it's so difficult to reproduce the exact arrangement of every shell. And of course, then you also have to reproduce the properties of every shell. So effectively, it's really unclonable and tamper-proof. It is so difficult to reproduce that we argue that not even the producer can make a second copy. And that is a big difference from most anti-counterfeiting solutions, which are based on secrets. So they can make like holograms in the credit cards and so on. They can make millions of copies. They just try to make it to keep it secret how to make them. But in this case, you even if you know everything, you can't make a second copy. So that's about the anti-counterfeiting and track and trace. I didn't say explicitly about the track and trace, but because you can identify the uniquely which item is which, you can track items through the supply chain, which is really, really important in order to avoid that that an original at one point of supply chain, for instance, in production in China, ends up being replaced by a fake somewhere where the customer needs it. So the second application area that we're working on is maybe even more exotic from this point of view. And this relies on the central reflection spot. So because these are spheres, they're actually retroreflectors. So no matter in what direction you are sending light into the sphere, you're getting light back to the light source. And retroreflectors, we know them, we have them everywhere, right? We have them in road signs, we have them in fancy clothing, we have them in safety vests in your cars, but these retroreflectors are indiscriminate retroreflectors. They reflect all light. They reflect white light. So that's why they are so incredibly bright. Now, if you make retroreflectors using cholesteric liquid crystals, using CSRs, then we can tune the retroreflection to be in the blue or in the red, or the most important, in the infrared or in the near ultraviolet. What that means is that we cannot see them, but a simple machine vision system can see the reflections. And in addition, as I mentioned, these are circularly polarized, which means that we can use the principle that is used in 3D cinemas to select what we want to see. And this is an example of how this works. So here is the same scene filmed through two cameras. Here it's filming through a right-handed polarizer. Here it's filming through a left-handed polarizer, and this liquid crystal is left-handed, so you see the color here. And here you see the result, which of subtracting this video feed from that video feed. Sorry, I think it's the other way around here. It's this video feed from that video feed. And what you see here is that the background is gone because the world is not circularly polarized. Very little in the world is circularly polarized. So that means when you do this subtraction, most of the picture of the image is identical in the two video feeds, so that's gone, and only the cholesteric is left. And this works in real time. So as 𝗺𝗃𝗃 in this case is moving this sheet, you see that the background is constantly gone, and you only note the reflection from the cholesteric. So we don't want to make rectangles with this, but what we're targeting is to make these kinds of patterns that you see here in this movie from Boston Dynamics. You see that the robot is interacting with its environment that is labeled by these black and white markers. They look a little bit like QR codes. They're called fiducial markers, and they are enormously helpful in letting robots, as well as augmented reality, interpret or what they are seeing in terms of what item is this, where is it, how is it oriented with respect to me. But you never see these in human populated areas because these are big and very visible. So what we are going to do is we're going to make them invisible. So just first, this is not an invisible one because we didn't yet have infrared or UV seeing cameras on this device. So here's just an example that the background subtraction works. So here is this is a marker that we made in this way with CSRs. And this is in the channel that blocks the reflection. This is a channel that sees reflection. And here you see the subtraction. And again, the background is gone and only the marker is visible. And just to show you that we can really make them invisible, here we have made a marker that is for reflection in the near UV. This is how humans see it. This is a regular iPhone camera. And the marker is here. It's almost impossible to see it. And then here we use the camera where the UV blocking filter has been removed. And there you can see when the UV light is turned on, the marker pattern is very visible, although for the iPhone, you still cannot see it. You do see a bit of blue light here, but that's because the light source is actually containing visible violet. So that we just need a better light source. And here you see the marker placed on a regular magazine. And just to show you that it's really very difficult to see it. This is a handmade, very manually made marker, so there's still a lot of defects. So you can spot it when you zoom in, but it's really quite difficult to notice it. Okay, so that's the kind of applied motivation to why we are making these things. So how are we making them? Well, at the moment, we are using a setup that was originally designed in the David Waite group at Harvard that a lot of people are working with. So maybe many of you know it already. So we put two cylindrical capillaries that are tapered against each other from opposite side inside a square cross-section capillary. And we pump the inner water phase that forms the internal droplet into one cylindrical capillary. And then we pump the liquid crystal in the voids surrounding of the square capillary surrounding the cylindrical one. And from the right, in the same square capillary, we pump the water phase that is going to be on the outside. And then we can collect the shell suspension here in this second cylindrical capillary, because this capillary injects the internal water phase into the liquid crystal flow that comes here, and then this water flow, because the water doesn't mix with the liquid crystal, it flow focuses this double droplet, if you like, into the collection tube. So the devices that we make look like this. They're very handmade. It's convenient because you can really tune them as you like. This is, again, from the Harvard group design. A lot of glue is being used, and sometimes they don't quite work out, and every device has its own personality. So we're quite happy that Fluigent, together with Sequoia, is now introducing a commercially made device for making these double emulsions. But we'll come back to that in a moment. This is just a movie showing how the production of the shells is going. So you see here's the injected water droplet. Here comes the liquid crystal surrounding it, and the outer water phase here is flow focusing the whole emulsion into the collection tube. So after production, this is what cholesteric liquid crystal shells look like. That's very different from what I showed you before. And that's because this arrangement that I draw in the cartoon with a helix exactly in the radial direction, well, that doesn't happen right away, because this production process gives you a very unaligned or disordered liquid crystal shell. So this would be pretty useless for applications. But the nice thing is, because they are shells, you can actually drive water into the core from the outside by using osmosis. So the shells are not impermeable. They're immiscible with water, but they're not impermeable to water. So if you have a little bit more of PVA inside than outside, then you have an osmotic pressure that drives water into the shell. And that means that we can actually anneal these shells fairly quickly. So this is from 2016, and Young managed to reduce the annealing time from a week down to about 12 hours in this way. And with our most recent result, we've actually reduced it to 6 minutes. So by optimizing the material that you use for osmosis and optimizing the liquid crystals, you can make this process much faster. And basically what it's based on is that this stretching that the osmotic flow of water gives rise to that compresses the shell and therefore aligns the helix in the way we want. So you see, you get the nice optical properties fairly quickly in this way. So finally, we need to turn these into polymers, right? Because this is still a liquid, so if you cannot work with it like that. And that has a very interesting consequence. So this is a side view of what the polymerization looks like. So remember, gravity acts on these shells, and they are then always thicker on one side and thinner on the other. So in this case, the inner droplet is lighter, so it rises up, and you have a thin top and a thick bottom. And the polymerization is triggered by shining UV light. There's a photoinitiator inside. And when these acrylate monomers polymerize, they shrink. But they now shrink around a water droplet that is incompressible, that does not want to shrink. So what's going to happen? Well, this is a movie. It's a real-time movie showing what happens. The shell simply bulges out at the thinnest point in order to allow the too large inner volume to still fit. Sometimes they even break during polymerization, but in most cases, they just have this bulged out shape. So what we do next is that we put them in an acetone bath. So here you have the polymerized shells with the bulged out section. And this is still in water, but then when Young adds acetone, you see that the swelling induced by the acetone, the swelling pressure, just pops off the thinnest part that simply cannot support the swelling. And that is really, really interesting, because that means that every single shell has a single hole. Now, these look as if they would be they're not spherical anymore. That's because because we're filming from the side, the shells are collected at one point of the capillary, and there the curvature of the capillary creates an anisotropic lensing effect. They are spheres, as you can see in this SEM image. And you can see it's really amazing. You have a bunch of spheres where every single sphere has exactly one hole. And that's thanks to this polymerization and washing procedure. And this is really important, because if you look at these bunch of shells in optical microscopy, it's exactly the same sample. You see in reflection, you see that they have these nice properties that we want, with the central reflection and the communication and so on. But in transmission, you see there's a lot of scattering. They're really dark. And why is this? Well, that's because we need a stabilizer for making the shells using microfluidics. And that's, in this case, it's polyvinyl alcohol, or PVA. And PVA isn't soluble in acetone. So it makes this layer of crystalline PVA or amorphous PVA on the inside and on the outside. And on the outside, in this case, it's gone because of the first washing with water before adding the acetone. But on the inside, it remains. So, but because we have this hole, we can now wash a second time with water. And then you see the scattering is basically gone. We get this very nice, smooth shells that have these fantastic optical properties. So apart from the scattering from the PVA being gone, we can now fill the shells, the empty shells, because we have the hole, with an index matching fluid, because that's also critical. If you want to put them in a binder, the binder has to be index matched to the shells in order not to have scattering. And that's the reason why we can make these markers so invisible to the human eye, because we have this one hole in every shell, and we can fill with an index matching binder as well as surround by an index matching binder, and we can get rid of all the stabilizer residues. Okay, thanks a lot. That's what I wanted to say. So now I hand over to Fluigent, so they can tell you about how to replace our handmade device with something that looks a bit nicer.
Thank you, Jan, for that. I will take over then and share my screen. I hope everyone can see the screen. So as Jan presented, he's using an homemade device based on the alignment of two capillaries, glued together to make a double emulsion. And the idea today is to present you a new device that we have developed in collaboration with Sequoia called the Ray Drop. So the ray drop is basically based on the same principle that you have seen during the presentation, during Jan's presentation. So it's based on the combination of a co-flow and 3D flow focusing. Here, the difference is that it's embedded in a non-confined metallic chamber. So the idea is to have this device, so metallic device, which will contain a chamber. And inside this chamber, you have two capillary aligned. So you can see that you have an injection capillary composed of two nozzles of a big, let's say, of a double emission nozzle, a big nozzle here, aligned in an extraction capillary. Those two capillaries are immersed in this chamber, which will be filled with the continuous phase. So the continuous phase is injecting it inside the chamber. We will regulate the flow rate inside the continuous phase. And then we will inject also the core phase and the shell phase, which are redirecting inside this double emulsion nozzle. If we focus a bit on the double emulsion nozzle and the extraction capillary, we can see that the double emulsion nozzle is composed of two nozzles, one nozzle in order to carry the core phase, and an external nozzle which carry the shell phase. And the idea is that we are going to regulate precisely the flow rate of the continuous phase inside the chamber, the shell phase, and then the core phase. And by a combination of specific flow rate for the three phase, we are able to generate double emulsion like this. So the really good advantage of this technology is that it's based on this axisymmetric geometry that allows to generate different type of emulsion without any coating needed. So that means that we can generate double emulsion without any coating or surface treatment on the channel wall. This is made because here the continuous phase is always surrounding the double emulsion, so the shell phase and the core phase, and you never have any wettability issue because you do not have any contact between the core and the shell phase with the channel walls, which are here a glass capillary. So basically, the ray drop is a really robust and versatile tool. As you can see here, it's totally possible to disassemble the ray drop. So it's composed of three main elements. You see the insert for the injection capillary here. Here you have an insert, and on this insert you have the injection capillaries composed of the double nozzle, and you have another insert for the collection capillary where the extraction capillary is mounted, and a chamber. You can remove these two capillaries, these two inserts, just by removing those two screws quite easily. So you can, for example, if you want, we can provide different size of the double nozzle, for example, and extraction capillary. So you can go from one size to another quite easily, and you can do it on your own. You do not need to send it back at Fluigent to make the replacement. You can just change easily the insert. This is something which is really useful when you want to target different droplet size, double emission. But it is also something which is really interested when you want to make other emulsion, such as single emission. This is also something which is possible. We have an insert for that. So you do not need to buy another ray drop. You just need to change this insert, remove the same way the double emission nozzle insert, and replace it with a single nozzle insert, where you will carry only the dispersed phase here. Continuous phase will be the same. And you will have mounted of this insert one single nozzle to make simple emulsion. So as you can see, this is a robust device that is easy to handle, and you can disassemble it really easily, and you can clean it then if you are making different type of experiments, such as, for example, let's say you are making water in oil in water emulsion, but you also want to make the opposite oil in water in oil emulsion. This is possible by cleaning totally the device. And for that, disassembling the device is also a good opportunity for that, to have a better cleaning. Okay, in terms of capabilities, the ray drop, the ray drop, as I said, is based on this geometry. You do not need any surface coating to make double emulsion. So that means that you can make different type of emulsion, such as water in oil in water double emulsion, but also oil in water in oil double emulsion, and partially miscible double emulsion with the same device. You do not need to change any device. You just need to clean it. to go from one type of emulsion to another. We have tested different types of emulsion for water in oil, water in 𝗎surf in water. 𝗎surf is a surfactant from Fluigent, which is used in fluorinated oil, HFE 7500. We have used also water in mineral oil with a span 80, for example, as surfactant in water, but also the opposite, mineral oil in water in mineral oil. We also have used partially miscible solutions such as solvent. Here we have used ethyl acetate, water in ethyl acetate in water. This is something which is really useful when you want to make polymer microcapsule, for example, where the polymerization is made by solvent evaporation. So it's something which is really useful for encapsulation of active ingredient inside a biocompatible microcapsule. And for example, you have an example here where we generated double emission using a polymer shell and a core solution. So this is the kind of double emission that we can generate on this small video. So this is the capabilities of the red drop. But something which is also really important is to play with the shell thickness. So with the red drop, you are able to play really precisely with the shell thickness. As you can see on this picture, we have made different type of shell thickness here, which is a bit larger, smaller shell thickness, and even really, really thin shell thickness. So it's something which is really useful. And also for that, you need to have a really good fluid handling solution. That's why we are proposing also the red drop in combination with our pressure-based flow controller to have a good stability and a good precision to handle this kind of operation. So this is for the key features. In terms of performances, we are able to generate around kilohertz double emission. So this is the frequency that we are able to generate with a red drop double emission, for example. In terms of size, we are able to generate from 80 to 150 micrometer, but it's also something for the standard red drop. So standard red drop with a standard size. In fact, it's totally geometry dependent. That means that if you want to make a bigger double emission, for example, with a bigger shell and a bigger core, it is something which is possible. We will just need to change, as I said before, the double emission nozzle, which is with a certain size to have a bigger size, and extraction capillary as well with a bigger size to target bigger double emission size. It is also possible to decrease as well. And actually, we can go from 80 to 450 micrometer at top, let's say. Well, it depends, of course, of the fluidic property, so regarding the viscosity and so on. But also, we are able to decrease the size to 40 micrometer, and this is something that is made by a specific geometry as well. And using all this, let's say, technology, so the red drop with fluid handling system in combination, we are able to target to generate really highly monodispersed droplet with a polydispersity lower than 2%. Okay, now we will focus maybe more on the experimental setup that we are proposing at Fluigent in collaboration with Sequoia. And I will let Malik describe a bit the setup and also the project.
Thank you, Adam. So as Adam says, Fluigent is specialized in one technology, which is the pressure controller. We develop and manufacture our own pressure controller for microfluidic devices at our office here in Paris. So in association with Sequoia and the red drop chip, we develop several packages in order to do application like Adam explains, as double emulsion and single emulsion production. So the setup, the schematic that you see is one setup that we developed with Sequoia in order to produce double emulsion droplets. So as you can see in this schematic, you will have on the bottom left our pressure controller, as I say, which is our main technology. So this pressure controller will apply through pneumatic tubing in a reservoir a certain pressure. This reservoir will contain a solution which will be pushed through a microfluidic tubing through another flow rate sensor. So one of our big technology is the fact that we can associate our flow rate sensor directly with our pressure controller in order to either control in pressure the solution flowing inside of our tubing, or to control directly in flow rate the solution that is flowing inside of our system. So thanks to an algorithm that we develop, the flow rate will be increased or decreased accordingly to the value that we want to achieve, and the pressure, as it's directly linked to this flow rate, will do the same thing. So for this setup, in particular, we develop we choose to use 3 different pressure controllers, one for each phase. So the first one will be used for the continuous phase, the second one and the third one for the shell and the core phase. So for the continuous phase, we use one reservoir of 50 milliliters, and for the core and the shell phase, we use 2 reservoirs of 15 milliliters. So using 2 reservoirs of 15 milliliters for the shell and the core phase will allow the user to choose between 2 different solutions during its experiments for doing directly its double emulsion shell and core phase. So by using a system of valve, you will be able to switch between one solution or the other accordingly to what you want to do at this point. Just after those reservoirs, as I say, you will find our flow rate sensor in order to control the system in flow rate. And after those flow rate sensor, you will find a panel of valves in order to prime the solution inside of the rate drop and make the droplet generation more easy. So how you can imagine that the microfluidic system without all those tubing can be quite complicated. So in association with Sequoia, we developed the platform that you can see here in picture and next to Adam and I. So this platform will contain all the devices that I just explained to you, but in a more simpler way. So you will find the pressure controller on the bottom left, just on top of them, the panel in order to choose the flow path inside of the ray drop. Just on top of this panel, you will find the reservoir that I just talked to you. On the right part of the platform, you will find directly our optical system in order to appreciate the droplet generation inside of the ray drop. So maybe you can find, unfortunately, we are not able to do any demonstration with the platform today, but we did another webinar yesterday where we used the platform and show how it works regarding the size of the droplets and also the valve system to show how it's simple with the platform to produce double emulsion droplets. So we will forward you a link to this workshop. So if you are interested in the platform, feel free to watch it, and you will appreciate the platform working. Thank you.
Okay, thank you, Malik. Maybe we will go with Shu now to present the result that she had made during her experience with the platform, actually.
Yeah, thanks. I will try to share. So as Yang introduced before, there's a huge application potential for the fiducial marker made by our cholesteric spherical reflectors. So it's necessary to find a standard mass production of cholesteric spherical reflectors. Now, now I'm mainly working on use the rejob platform to making the cholesteric spherical reflectors. In this presentation, I will give a brief introduce of it. To compare or divide our handmade device with rejob device, here is a rejob device. Let's have a close look of the inner structure. Here is the inner structure of the rejob device, and here is our handmade device during our production. And we can see the shell face in the rejob device is confined by the to solid wall. Well, or in our handmade device, there's the shell face is only controlled by the comparison of continuous flow and shell flow. So rejob device can will these two walls will enhance the stability of the production and will produce monodisperse shells. And another thing is our handmade device is unrepeatable because the whole device making process is mainly produced by hand. So it's really hard to produce two handmade device exactly same size at the exactly same size. And with rejob, we can make much smaller shells. With handmade device, we can produce shells with diameter 200 micrometer to 350 micrometer. And with rejob device, as I introduced before, the shells can be around 100 micrometer. So we really hope to use this rejob device to achieve the mass production of our of the monodisperse cholesteric spherical reflectors. Of course, we also face some challenge when we change the production to new platform. Before our production with handmade device, it's under 50-degree temperature, but with this platform, there's no heating system. So we need to think about to improve our mixture working at the lower temperature and also design a heating system suitable for the rejob device. In the meanwhile, we tried other liquid crystal to produce shells to practice the using of rejob platform. In the left video, here we try to use 5CB to produce liquid crystal shells. As we can see, it works well. Then we move to a higher viscosity liquid crystal E7 and mix it with 𝗪𝗪𝗪𝗪 R5011 to make it into cholesteric liquid crystal, and the production also works good. And but you can see when I tune the liquid crystal flow, sometimes it will sticky some liquid crystal on the collection tube. In the end, this video shows us how this whole rejob platform works in our lab. We hope it will produce in the end will produce the cholesteric spherical reflectors with this platform. Thank you very much.
Okay, thank you, Shu, for that. So now it's time to switch to the Q&A session. So if you have questions, feel free to ask. We already have some. So the first one is from Tommaso. Thank you very much for the fascinating talk. What gives the planar alignment at the interface? Maybe Jan or Shu, you can answer that.
Yeah, maybe I can go at that. So fundamentally, it's actually the water. So the liquid crystal is anisotropic, and that includes the interfacial tension. So if you have planar alignment, that has a different interfacial tension from homeotropic alignment, or radial alignment, let's call it. Tangential. So for a general audience, planar alignment is, we can call it tangential, and radial is perpendicular. Which alignment you get depends on which interfacial tension is lower. And if you just have these liquid crystals in contact with water, it depends on the liquid crystal, but most liquid crystals in direct contact with water, they will have a lower interfacial tension if the molecule, if the director is aligned tangential to the interface, and therefore you get tangential alignment. Now, in addition, we add polyvinyl alcohol to the water phase, and that is mainly for stabilizing the shells to make sure that they don't collapse and that they don't merge, or collapse into droplets and they don't merge with each other. There is still a discussion of whether the PVA itself is enhancing the planar alignment or not. I think it's not a big deal. I think the main issue is water. Of course, the best solution for stabilizing is to use surfactants. Adam mentioned the what are they called now again? The fluorinated surfactants that they have, and the surf, exactly, desurf. The problem with surfactants for us is that surfactants tend to induce radial alignment. Then if you have a surfactant, then the interfacial tension is smaller for the radial alignment, and that's the opposite of what we want. So we unfortunately, we cannot work with surfactants, but with PVA, we can get fairly decent stability also.
Perfect. There is another question. Do you heat the LC during the emulsion production? Should you heat the reservoir too? If yes, how do you do that?
Maybe I can answer this question. Yes, for some liquid crystal, when it hits the device, for this rejob device, we are thinking to use silicon heating matter to attach it on this rejob device to give it to increase the temperature of the whole device. And for heat the reservoir, we are thinking to design a whole chamber, put the whole platform in the chamber and heat the whole chamber to make the temperature uniform in this whole platform. I hope this answers your question.
I can also just make a comment. So one of the reasons that I decided to go for Fluigent when I started with microfluidics, because a lot of people are using syringe pumps, is that we can use basically any vial, any container we want, right? So before I came to know about the Fluigent systems, I did some electrospinning work with syringe pumps, and we managed to get the syringe pump out of order a couple of times because we had to heat the whole syringe pump. Luckily, it didn't break, but it just stopped working because of overheating. And that's a very nice thing. Then you don't have that problem. So far, we have aluminum blocks where we have drilled holes. And these holes were then of a typical sizes for glass vials that we were working with. And now we will probably make an updated version of this that then is adapted to the Falcon tubes that work very well with the Fluigent reservoirs here.
Yes, thank you, Shu and Jan. In the meantime, also, I wanted to present you something as well. Another slide that we have prepared is, so as I said before, with the rejob are able to go from 80 or up to 150, maybe more. But with 𝗺is working on different solution to decrease this size. We know that double emission size can be hard to decrease sometime. And there is a huge interest when you want to encapsulate, for example, other type of ingredients such as cell, living cell, or so on. It's really important to have, for example, in fact sorting, when you want to sort inside files, you need to have small double emission. So we are working, Sequoia is working on a new different geometry, and we are able to go down to 40 micrometer double emission. The idea is a bit different. As I presented, the rejob is based on the alignment on one nozzle and a capillary, basically. Here, the idea was to remove the extraction capillary, as I said before, quite easily by just unscrewing the insert, and place another nozzle, a counter nozzle in front of it, to increase the shear stress locally. And using this geometry, we are able, and by playing with the flow rate, of course, we are able to really decrease drastically the double emission size. So we were able to generate double emission around 40 microns. This is something that I wanted to also show, because this is something that we have worked on, and we are still working to improve it. So decrease again the size to go down to 40, for example, double emission.
That's really nice. I'm looking forward to that. Just one comment also from my side. When maybe you noticed in Shu's videos that the first liquid crystal shells were made with a liquid crystal called 𝗵𝗶𝗶. They look very transparent, whereas the second ones, they were completely black. And this black appearance is not because the liquid crystal is black, it's because of scattering. So, and that difference in scattering tells that the 𝗵𝗶𝗶 was probably actually in the isotropic phase. So one thing I didn't go into is that liquid crystals, if you heat them, they go into a phase where they behave like any regular oil phase, an isotropic phase. And 𝗵𝗶𝗶 has a very low temperature for that transition. So often just the heat from the lamp, for instance, can take the system over that transition, and then it behaves like an isotropic fluid. And it's something we haven't really investigated, but I'm pretty sure that the liquid crystalline aspects of the viscosity also play a very important role. So a liquid crystal actually has 5 viscosities. So because these are anisotropic, in contrast to a regular isotropic liquid that has 1 viscosity if you take regular shear flow, for instance, you need 5 different viscosities to describe the behavior of a liquid crystal. And then on top of that, you have elastic behavior that is very different, and that will affect the breaking of the droplets and so on. So I think much of these problems that we saw in the second video will be resolved simply by heating a little bit and by tuning the mixture so it has a lower clearing point.
Okay, there is another
question.
There's, yeah.
Well, that's for Adam, I think.
Yeah, okay, thank you, Jan. Are the capillary reusable and washable, or should you change capillaries each time? It's a good question. So it depends on what you want to do actually. It depends on the application, but the capillaries are reusable and washable. If you want to clean it, we have different protocols that we have developed to clean it. If, for example, you are using really strong polymer and you have sometime clogging of nozzle, it's not totally, let's say screwed. You can rinse it, you can wash it quite with different protocols, and you can either, if it's really clogged, you can put the rejob inside ultrasonic bath, which can help remove the polymer, or you can use also solvent to unclog the nozzle or the channel. So it is something that is also really useful for cleaning. Yes, it's possible.
But this is really one reason why we are so excited about the ray drop, because as Shu mentioned, it's when you make these devices by hand, you cannot repeat one device a second time. There's always a lot of variation. And one of the most critical things, the video she showed, the injection capillary was very nice centered into the collection capillary. That is one of the most critical issues. And that doesn't happen always, unfortunately. So quite often the injection capillary is a little bit off from the collection capillary, and then you can get very different results.
Yes, thank you, Jan. Okay, someone has raised his hand. Tommaso, now you can turn on your microphone, and you can ask if you want.
Do you hear me?
Yeah.
Yes.
Okay, great. So I can speak live and not write the questions. so really, thank you very much for the talk. I really appreciate that. And as a liquid crystal lower, I really appreciate that. I have a question on the surface tension, on the formation of the Janus droplets. Okay, it's a matter of surface tension and how much the viscosity and the elastic constant of the liquid crystal impact the formation of the Janus droplets. This is the first question. And the second one is on the fingerprints that you said you can use for to tag objects. Is the thing, as I understood, the fingerprints is dependent on the angle of observation? Is it right or not? So how do you solve it when you have a drone or a robot that has to identify something?
Yeah, so thanks a lot. Great questions. The first one, the Janus aspect is not related to the surface tension, but just to gravity, actually. So I think, who is that? There is an American group that created Janus particles from microfluidics produced shells, where they indeed had different alignments, I think, at the different sides. But they used a combination of fluorinated surfactants and so on to achieve that. In our case, it's not a Janus particle in the sense that the alignment is different. It's just a Janus particle in the sense that the thickness is very different. So because the inner droplet sinks or floats in gravity, then the one side is much thicker than the other. And actually, the thin part is so thin that light really goes through. And that's why it's a Janus particle in the optical behavior, not in the structure, so to speak, not in the interface. If you would just look at the interface only, it would be the outside interface would be the same everywhere. But the light sees a very different object if it interacts with the thin side or from the thick side. And of course, after polymerization, it's even more Janus-like, because then the thin side breaks and then you have a hole rather than just a thin side. So it's really different. For your other question, yeah, indeed, you have a very different behavior when you change the illumination conditions. That is, as you point out, that it's a challenge. On the other hand, it's also a very big advantage, because that's actually one of the reasons that you cannot just easily simulate these fingerprints. Because if there was no dependence on illumination angle, illumination and observation direction, then you could just record a photo and you can trick a system that you have the original object by just showing the photo. But the reason that you cannot do that is that the actual system depends, the actual output depends on how you illuminate and how you image. So when you want to record this, then it means that if you want to record the fingerprint, you have to make sure you get reproducible imaging and illumination conditions. Now, for the drone part, that looks at the markers from a distance. There, they actually don't see these fingerprint features. They just see the retroreflection. So there, you don't see the individual fingerprint. You just see the marker pattern that we have designed, that should be the same every time. So if you want to record the fingerprint, you have to go close, and you could do that with the drone as well. But then the drone has to be close and at a very specific angle, and you have to have a reproducible illumination and imaging system.
Thank you very much for the very clear answers. Thanks. Thanks again.
I think we do not have any more questions.
Thank you.
Thank you, everyone. Have a good day. Bye.
Okay. You too. Take care. Bye.
Goodbye.